Welcome to Basics of Finite Element Analysis Part 2. Today is the 5th day of 6th week of this course, and what we will start discussing today and also probably tomorrow is how do we actually evaluate the boundary integral which appears as Q term in the element level finite element equation. So, that is what our focus is going to be, that is we will learn how to evaluate boundary integrals for finite element equations. So, our finite element equation for the eth element looks something like this. Here elements of K matrix and elements of F vector, they are calculated using surface integrals, because we are integrating over the domain, and if the domain is a 2-dimensional domain, then they are evaluated using surface integral approaches. But to calculate this, we have to use a boundary integral, because Qi for the eth element is defined as Qn psi I ds evaluated on the boundary. What does that mean? So, suppose I have a triangular element . So, this is node 1, 2, 3, then Qn represents the flux. For instance, if it is a heat conduction problem, it is the flow of heat in the normal direction, in the direction normal to line 1, 2. Similarly, over line 2, 3, this is the direction of Qn. Similarly, for line 1, 3, this is the direction of Qn. So, Qn represents flux. In case of heat transfer, it could remain, it will tell us how much heat is getting transferred across this boundary 1, 2, 2, 3 and so on and so forth. So, for a triangle element, what do I have to do? I have to integrate from 1 to 2, this whole term. So, and ds is, what is ds? ds is a small line element. So, Qn could be flux per unit length, and if I multiply it by ds, it is the total amount of flux which is crossing the ds element. So, when I integrate it over line 1, 2, it is the total amount of flux which is getting out over line 1, 2. Okay. So, going back, Qi will be integral of this term Qn psi I ds over line 1, 2 plus same thing over line 2, 3 plus, so this is 2, 3 and plus the same thing 3 to 1 of ds. Okay. Now, consider a domain. So, let us consider this domain and I can break this domain . and okay. So, this is the physical domain, which is the purple boundary, the actual domain. I have discretized this domain into a large number of elements. Now, we will consider two elements. This is element 1 and this is element 2. So, I will draw these two elements separately. So, this is element 1 and this is element 2. Okay. Element 2 is having two neighbors. Element 1 is having neighbors on all the four sides, on all the three sides, I am sorry. So, element 1 is surrounded by elements all around it. Element 2 is surrounded by elements only on two sides. The third side is exposed to the outside. Okay. If I have to calculate Q for element 1, so let us label these. So, let us label these nodes A, B, C, D. These are nodes. So, the boundary terms for element 1, the boundary terms will be A to B plus B to C plus C to A. These will be the three boundary terms using this expression here. Okay. So, these will be for element 1, these will be the three boundary terms, Qi will be this. Let us also actually make another two more elements, 3, 4 and 5. Okay. Now, so this is for element 1. What will be the terms for? So, I will put two more nodes. So, D, E, F, G. Okay. For element 2, element 3, what will be the for element 3? Qi will have three components, B to C plus C to F plus F to B, right. And then for element 4, Q vector will be integral of C to A plus A to E plus integral of C to E plus E to A for element 4. And for element 2, what will be the thing? Qi will be A to D plus D to B plus B to A. So, what I have written down is boundary terms for element 1 and its neighbors. Element 3 is a neighbor, element 2 is a neighbor, element 4 is a neighbor. So, I have written boundary terms for its neighbors. Now, what we see is that you have, so these are at the element level. So, these terms will appear at the element level, right. But ultimately what do? We assemble these elements together, we assemble these elements together. When we do the assembly, what happens? This term A to B also appears for element 2, right, but there the sign will be reversed, there the sign will be reversed. What does that mean? That A to B is this line, A to B is this line. For element 1, the flux will be happening in this direction, outwards. For element 2, the flux will be happening in this direction, okay, again outwards. So, as a consequence, when I do the assembly, these two terms will add up and their total will be 0, okay. Similarly, the terms corresponding to B to C, so B to C is the interface of element 1 and 3. So, this term will cancel with this term, okay. And C to A, C to A is the common boundary between 1 and 4. So, this term will cancel out this term. So, what I see is that because an element is surrounded on all other side, its 3 sides by other elements, when I do the assembly, the boundary terms will add up and their total will be 0, okay. That will be the case for an element if its boundary is surrounded on all the 3 sides or on all the sides by other elements. That is for an element which is in the interior of the domain. So, for elements interior in the domain, Qi's cancel out at assembly level. They cancel out at the assembly level. So, if they are going to cancel out at the assembly level, then what is the point of calculating those boundary terms, right? There is no point in calculating those boundary terms for interior elements. But for elements which have an external boundary Qi does not cancel out on non-shared boundaries. This is important to understand. So, let us look at this picture again. So, for element 1, all the 3 boundaries A, B, B, C, C, A, they are shared with other elements. So, at assembly level all the Q's will cancel out, but for element 2, Q's will cancel out for boundary AB, they will cancel out for boundary BD, but they will not cancel out for boundary DA, because that is not a common boundary to more than one element, right. So, here Q does not cancel out. So, we have to calculate Q only for this boundary, okay. So, we have to, in the overall mesh, we have to look at those boundaries which are exposed and which are not shared, and we have to calculate Q's only for those boundaries. This is important to understand. So, that is what we will do. So, that is what we plan to do starting today. Okay. The other thing which we should note is this is a boundary integral. So q is a boundary integral, right. We are calculating this q on the boundary. It is a line integral or a boundary integral. For 2-dimensional surfaces, the boundary integral becomes a line integral. For 3-dimensional surfaces or 3-dimensional systems, the boundary integral becomes a surface integral. So here it is a line integral, and we will see that essentially what that means is that for calculating this boundary integral, we only have to worry about 1D elements, because it is just a line, it is not a surface. To calculate integral over this entire domain, it is a surface, so it is a 2D element, but here we are only calculating the integral in one dimension, which is this particular dimension. Okay. We are only calculating the integral in this dimension, which is dimension along AD. Okay. So, this is important to understand. So, that is what we plan to do. So, what is our aim? Our aim is to figure out how do we calculate line integrals around a specific boundary of a element, and in this case we will start with a triangular element and figure out how to calculate the line integral. So, this is my global coordinate system x, y, and this is my triangle. So, we have side 1, side 2, and we have side 3. We have node 1, node 2, node 3. The global coordinates of this are x1, y1, x2, y2, and x3, y3. x1, y1, x2, y2, x3, y3, they are the global coordinates. Now, we will also develop a local coordinate system. So, the local coordinate system, this is one axis S, and there is another axis normal to it, this is axis T. Okay. So, this local coordinate system, important to remember is aligned to side 1, 2. So, it is aligned to side 1, 2. Here my interest is in calculating the boundary integral if I am calculating boundary integral along side 1, 2. Okay. If I was interested in calculating boundary integral along side 2, 3, then my S axis would be along line 2, 3 and my T axis would be normal to that, understood, and the origin would lie at node 2. If I was interested in calculating the boundary integral along line 3, 1, because I am interested in calculating about specific boundaries, then in that case my S axis would be in the direction of 3 to 1, origin would be at node 3 and the second axis would be normal to that S axis, understood. So, this is not exactly normal, so I will make it a better normal. So, this is T axis. So, let us say this side A, side 1 is A long. So, my global, so it is A long. and this distance is B, which is parallel to side A, and this distance is C. Global and local. Okay. Global is x1, y1, and local is 0, 0. Global is x2, y2, and local is a0. And third one is x3, y3, and what is the local coordinate in that case? The value of S is C and this is B. Agreed? So this is the mapping for each of these nodes. Now what is our aim? Our aim is to find psi 1, psi 2, psi 3 along side 1. Okay. We are interested in finding psi 1, psi 2, psi 3 along side 1, because I am interested in calculating the boundary integral along side 1. If I was interested in finding boundary along side 2, then my local coordinate system will get reoriented and repositioned. So this is our aim. We want to find psi 1, psi 2, psi 3 along side 1. Why do we want to do that? Because in my boundary integral I have psi I, and if I am wanting to use local coordinate system, then I have to find the formula for this. Understood? And what about Qn? Qn would be known, right? Qn would be known, because only then way I can calculate. If I don't know Qn, then how can I calculate the boundary integral? So Qn has to be known. Then I can calculate the boundary integral. Okay. So this x1, y1 maps to 0, 0, x2, y2 maps to a0, x3, y3 maps to cb. Okay. So I have to, first thing is I have to find out some formula which transforms x into xy into st. Okay. And this is a linear transformation. So I can write x is equal to a1 plus b1 s plus c1 t, and y equals a2 plus b2 s plus c2 t. Okay. So this is the transformation. These equations transform a local coordinate into global coordinate and vice versa. Okay. But we do not know the values of a1, b1, c1, a2, b2, c2. So now we have to figure out their values. Okay. So we have 3 points. Using these 3 points we calculate these a1, b1, c1, a2, b2, c2 and c3. So now, this is our ultimate aim, to find size, but before we want to find psi, we have to know what is the nature of this transformation, right. So that is what we plan to do. So let us proceed. So when S is equal to 0, t is equal to 0, that is for node 1, x is equal to x1 and y equals y1, right. Actually this we have already written here, so I do not have to write it. So let us consider the first point for node 1. Let us consider node 1 and apply equation 1. what is the value of x for node 1? x1, and that equals, using this relation, a1, what is the value of s? 0, and so b1 times 0 is 0 plus c1 times t is 0. So a1 is equal to x1, and similarly for y1, now we use the second equation for y. So y1 for node 1, what is the value of y? y1, that equals a2, because for node 1 s and t are 0. So in the second equation, which is this, y1 equals a2. So we have figured out what is the value of a1 and a2. Now let us look at node 2. Node 2, what is the value of x at node 2? x2 is equal to a1 plus b1 times, what is the value of s? A, and what is the value of t? 0. So this gives me b1 equals x2, and what is a1? a1 is x1, so minus x1 divided by a. Similarly, y2 is equal to a2 plus b2a, so I get b2 is equal to y2 minus y1 divided by a. Understood? So this is the thing for node 2, and for node 3 the relation is x coordinate is x3, this is equal to a1 plus b1 times c plus c1 times b, and this will give me the value for c1, because I now know a1 and b1. y3 equals a2 plus b2c plus c2b. This will give me the value of c2. Okay. So what we have done is we have calculated the values of a1, b1, c1, a2, b2, c2, and we will use this information to calculate first the psi functions and then use those psi functions for calculating the boundary integral. So that is what we will do, and that is what we will accomplish tomorrow. Thank you.